All right, welcome to the session on 10 cool things we can do with popular JVM languages. It's a pleasure to be here to talk to you about something that is exciting to go across multiple languages on the JVM. First question, of course, I would ask myself is, why look at some of these different languages? The objective is not to switch over to these languages, but to be able to effectively use these languages on projects where it may make sense. Oftentimes I view languages as vehicles. There are times I would want to take my bicycle, other times I take my car, other times I fly airplanes to get to distant places. So languages kind of give us that mobility. And one of the real nice things on the JVM is we can mix some of these languages together to put together applications. Sure, there's a learning curve when it comes to these languages, but if we can get beyond the learning curve, I think we can do some really interesting things. And that's what I want to point out here with some examples, things that have drawn my attention, things I think are pretty cool when we can mix these languages. So the very first thing I want to talk about is accessing a file. I want you to think about this just for a second. How do you read the content of a file in Java? Okay, that's not fun, is it? You have to first start a buffer stream, and then you have to connect a bunch of things to it. Are you done? No, then you start looping through. Are you done? No, you got to put all those try-catch blocks around your code. And by the time you're done, about 30 lines of code, right? So we don't have to go through as much effort to do it. So let's quickly look at an example here. I want to read exactly the same file that I have right now on my hand. So I'm going to say new file, and the file name here is called sample.groovy. And I'm going to simply say .text over here to get the content of that file. So in other words, right there is a little piece of code I've written to read the content of the current file and print it. So you can see that that's really very easy to just read the content. Now, of course, you may say, what about reading other files? If I want to read other files on my system, sure, I can specify, for example, over here, something along the lines of etc. Host, for example, and you can see that it brought in etc. host right away. But one of the things that Java tells us is, what if things go wrong, for example? Maybe I mistype this and I say etc. hots, and hopefully I don't have that file on my machine. And if I'm going to ask for that, what should happen? Well, maybe it's going to give me an error, but sure, it's going to be an error. Don't we have to deal with? Well, we have learned a hard lesson from Java. What does Java say? You will handle the exception. And the Java programmer says, run that by me again. Let me tell you who's in power, and puts an empty catch block, right? So there is no way to win this game. So these languages say, let's put the responsibility on the programmers. Let them do the right thing. So sure, if you mistype things, you can get an exception you can deal with it. You can put a try-catch block around it if you want to. So that's up to you, but it doesn't force it on you. Likewise, here in Scala, for example, I'm going to say, in this case, I'm going to go ahead and import, let's say, scala.io. And once I import it, the underscore simply is like a star that we use in Java, and I'm going to simply say I'm going to bring in the source dot from file, and in this case I'm going to specify the current file itself that I'm working with. So I call this sample.scala, and if I just run this for a second, you would notice it gives me a non-empty iterator, and then I'm going to call a make string on it and gobble up the content right away and bring it up, and that's a file being read right there. So you can see how it is very easy to do things. Now, why do I care about some of these? And the reason simply is, you're sitting on this Wednesday afternoon at work, and all of a sudden a light bulb goes in your head. Hey, wouldn't it be so cool to put this in this file and read it and parse it and do this? And you're like, wow, would that work? Yeah, let's try. And then the minute you start putting the try-catch block, it sucks the life out of you. And you're like, you know what, never mind. We can give this to an intern tomorrow, right? So the point really is, you want to get from this light bulb moment to trying something very quickly, and you want to try out things that can get your work done very quickly rather than delaying you and slowing you things down. So that's what we saw just now. I want to talk about starting a process over here. Well, before I talk about starting a process, let me talk a little bit about where I've used this, for example. I maintain a number of Subversion repositories. About 10 years ago, maybe about that time, I decided to do some work. For example, if John checks in a file, I want to immediately tell Sarah that a file has been modified so she can review it. When Sarah checks back a comment or a review, I want to go back and alert somebody else. So I set this up about 10 years ago. And this program I wrote for for doing this was a post-commit operation, had to apply rules to do this, and it was about 150 lines of code. In this 150 lines of code, a good 50 lines of code was just to say hello subversion and get the details from subversion. So it worked, and I was, I'm half smart, so I wrote it as a nice configurable program. All the rules as to who to talk to, whom to notify, what their email address are, all that is in a configuration file. So for a couple of years, I would just copy the configuration file and modify for new projects I created. But after about 3 or 4 years, I kind of was playing with this, and I said to myself, wouldn't it be kind of fun to try something a little different? I know you know this, but programmers will secretly admit to you there is more fun rewriting code than reusing code, right? So I decided I'm going to just rewrite this. So to rewrite this, I decided I'm going to use something very flexible, so that 50 lines of code to talk to Groovy. Take a wild guess how many lines of code in Groovy, for example. Anybody? 10 lines? All right, let's try it. So I'm going to create a string over here. Let's say svn help for a minute. And I'm going to say execute over here, dot text over here, and then just print it. And you can see that that subversion help being printed. And if you're such a fan of Git rather than svn, go ahead and try that out as well. And that's Git help. And you can call things like status, for example, what have you. So what am I really doing in here? Well, if I go back and say svn help for a minute, and only ask for not the text value, but if I just ask for the execute, you would be surprised it's really bringing in a process object. So they didn't do anything very different, but they just made things elegant so that we don't have to sit there and fight our way through. So they took the process interface and added a property for it, and so the text gives us the access to the standard output directly. Similarly, you can connect to the standard input if you're interested, and instead of calling txt, you could do error.text, and that gives you the standard output off the bat. So it becomes very easy to communicate to external processes, as you can see, and that fizzled to about 2 or 3 lines of code to get the whole thing done. I want to then move forward and talk about yet another thing, but this time I'm going to switch over to Java 8, because Java 8 has some really nice features for us to use. So I'm going to start with some little feature that I can use in Java. Let's start with a little example before we go further. I got a class called resource here in Java, and I have a constructor for this resource, let's say. I'll call it resource. And just for our purpose, I'll just go ahead and say output, and we'll say creating, for example. And I also have a bunch of functions I'm going to write. So function F1, and just for our purpose, I'll simply say over here, just say F1. And similarly, I have a function called F2. Now, imagine for a minute that this function I'm writing is, this class I'm writing is very expensive. It uses some external resources. So to take care of proper cleanup of these resources, I'm going to write a finalize method. And in the finalize method, just for us to know, I'm going to write a cleanup operation right there. So I'm interested in using what we just created. So I'm going to say resource, and I'm going to just create an instance of resource right here. And then I'm going to say resource.f1, go ahead and call resource.f2, and run the program. And you can see that it created the object called f1 and f2. Hey, but wait a minute, it did not really clean up the object. If I'm using an external resource that is very heavyweight, I didn't clean up. So my first suspicion is, darn it, did I mistype the method finalize? I take a look at it. No, it looks like I typed it properly. Well, then why did it not call the finalize method? Well, because we know that the garbage collector in Java is like the garbage collector in my neighborhood, right? It says, oh, forget Venkat, that's not important. We have other fun stuff to do. Well, the JVM garbage collector says, I've got a lot of memory. Why waste effort and interrupt threads and do all those fun stuff trying to run the garbage collection? Forget it, I'll run garbage collector when I really need it. Well, unfortunately, this can have some really bad ramifications. This brings back memories. I was called by a client and said, why don't you come over and do some code review? And while you're doing this code review, maybe you can help us find and fix a problem we've been having for quite a little bit of time now. And I asked the manager, what's the problem? And he promptly said, go talk to the programmers. So I went and talked to the programmers. And they all kind of gave different answers, but one programmer explained it the best. That programmer said, well, our program works fine most of the time. I said, that's great. Can you please tell me when it doesn't work? And he said, sure, it doesn't work between 7:15 and 9 in the morning. I said, that's awesome. Every day? He said, no, only Monday through Friday. It works fine on weekends. So I'm like, okay, what could be the problem? What's going on here? Well, it turned out it was an application running on a portal, and you can imagine what happens in a large company on a Monday morning through the week, 7:15 to 9 a.m., people walking into the company, logging on, accessing the portal, whether they want it or not. Resource contention. So I started digging into the code, and what I found out was, for whatever reason, in the constructor they had requested for a database connection, and in the finalize they were releasing it. Well, okay, there's a large amount of memory being used outside the JVM, but within the JVM there was only a small amount of memory usage, so the JVM said, forget it, no need to run the garbage collector, just hang in there and create objects, and exceptions were being thrown, not being properly handled through this code, and of course they were having this trouble. So once I found out what the problem was, I wanted to make sure this really is a problem before I really help them fix it. So I renamed the finalize to a close method. And once I renamed this to a close method, I just went ahead and called the close, and sure enough, the cleanup was happening and the connection was being released and all those good stuff. The programmers immediately looked at this and said, hey, it looks like this is working. We're not getting this problem anymore. So they were pretty happy. Well, as a matter of fact, this was kind of funny to watch, because that afternoon the boss comes back from lunch, and when he came back from lunch, of course, being a curious boss, he wanted to know how things are, and the team said, oh, of course, the problem is gone, we fixed it. And then, of course, he said, how did you guys fix it? And the team said, well, Venkat asked us to write this one line of code, and we added it, and the problem is gone. And what else did you do? And the team said, nothing else. And then I hear him whisper saying, well, if you added only one line of code, do we still need to pay him? Well, sure, right? So absolutely, we have to know what we're doing. Well, in this case, though, unfortunately, this is not a real good solution yet, because there is a possibility that this close may never get called. What could go wrong? That's correct. I heard the whisper called exception. So the right way to do this would have been to put a try block around this, and then you want to move this into the try block, and you want to say catch over here, and maybe throw in a little finally block rather, not a catch block. And the finally block you probably want to call the close method, and this would be the right way to do it. But this brings up one other problem. For this solution to work, you would need something that I definitely know I don't have. It's called the discipline. And I would remember only to do this very, infrequently, and most of the time I would forget it, and we will have bugs in the code. So what can we do to fix it? Well, before I talk about fixing it, let's talk about one other solution in Java 7. It's called automatic resource management. And what does automatic resource management do for us? It looks like a fancy word. Well, they gave us a nice, interesting tool. We can remove a little bit of ceremony from the code. So we can put a try block and put the resource right in there, and as a result, we can remove this finally block. Now, for this to work, unfortunately, we have to do a little bit more work. So we have to go back here and say implements over here. And in this case, I want to implement the auto-closable interface. And once I implement the auto-closable interface, on line number 16, it performs an automatic cleanup of the object when we leave the try block. It removes the ceremony of having to put the finally block. It nests the try blocks nicely and can do the cleanup. So overall, you would say, hey, this looks like a nice solution. Well, that is correct, except for one small problem. Remember what I said about my habits and discipline? So what if I come in and start writing code, and I totally forget to put the try block in the first place, and I end up missing out the try block entirely? What's going to happen? Because I implemented auto-closable, is it going to come and tell me, hey, you forgot to put the try block, you should use the automatic resource management? Well, guess what? It doesn't. So we are back to square one. But please don't act surprised looking at this, because you know this very well. You should never trust a feature with the word management in its name, right? So that's kind of obvious in this case. Well, okay, this doesn't work, but is there a way to make sure this absolutely works? There is no other way to make this work at all. Well, thankfully, we can do Java 8 Lambda expressions to make that work. Let's get back to the resource.close for a minute. Let's go ahead and remove this ceremony stuff. We want to get directly to the solution that works. So how do we really make this work? So as a designer of the class, there are a couple of things you can do. The first thing I'm going to do is mark the close method private. So the programmer walks along, tries to call the close method. The Java compiler gives an error saying you cannot access the close method. And if I were the programmer, I would say, cool, no worries, and I would move on at this point. Well, okay, but this doesn't solve the problem yet. The next step I'm going to take is make the constructor private. And now the programmer says, darn it, what does this programmer really want after all? I cannot create an object, I cannot clean it up. What is the magic? Now we make the programmer think a little bit. So what I'm going to do here is, I'm going to go ahead and write a method over here called let's call it a static method. We'll call it use method. You sure can return some results if you're interested, and you can try to extend this little pattern a little bit later. And within this use method, remember, I'm the author of the class resource. I'm keenly worried about resource cleanup. I'm aware of what I'm doing in this case as an implementer of resource. So I'm going to go ahead and create a resource object right here, and I'm going to put a try and finally block for once I can remember to do this. And then within this, I'm going to go ahead and close this. So notice in my use method, I created a resource, and we haven't gotten to what's happening right here, but we created a resource. But when we are done, whether we had an exception or not, we would take care of cleaning up this properly. So right in between these two operations, I'm going to go ahead and yield my little resource to a block of code. So I'm going to say, hey, block, would you please accept this resource and make use of it? So for this to work, where in the world is this block coming from? Well, to use the block, I'm going to use what is called a consumer, which is going to take a resource as an object. Well, consumer is a functional interface introduced in Java 8. So I'm going to go ahead and say function.consumer and bring it as an import right here. So I think we're almost there. So we have the use method. It creates a resource object, yields control of the resource to the accept method of the block, and then when it returns back, it performs a proper cleanup. So now I can go back to the code and I can simply say use, and within this code, I'm receiving a resource object, and then within here, I can put a multi-line lambda expression if I'm interested in, and I can wrap this code around that right away. So we can see what's happening in this case. In the use method, we are receiving an object that we want to use. We do whatever we want to do with it. And then when we are done with this, we are returning back to the caller. So the caller is responsible for creating this object properly, giving control to us to do whatever we want to do. And when we are done with it, it takes back control and performs a cleanup. Now, if you really think about it, this is not entirely new at all, but we are able to make use of this for our own code within Java 8. If you really think back about this, this was a pattern introduced back in the Smalltalk days called the execute around method pattern. And the execute around method pattern basically says there is a piece of logic you want to implement, but there is something that has to execute around it before and after. And if you really think about this, this has been around since Java 1.0 day. If you really think about synchronized, now synchronized gives you a block of code. It acquires the lock before you enter the block of code. And then when you leave the block of code, it releases the lock, even if there was an exception. So this concept has been around for a while, except we couldn't do it for ourselves. We had to only rely upon where it was provided as a boilerplate. Now we can create things like this for our own purpose and use it very effectively, as you can see in this example. Now, we looked at one other thing we can implement here in Java 8, which is a nice pattern we can make use of that comes directly from the lambda expressions we can make use of and implement very nicely. But I'm going to move on to something else that I want to show that I'm sure everybody in this room has done at some point in time or the other. Let's say for a minute I have a bunch of names on my hand. So I have names over here. Let's just go ahead and define a bunch of names. Let's say Joe, let's say Sarah here, and then let's say Jack and maybe a Jill over here. Now the problem given to us is we want to take each of these names, convert them to uppercase, and print them comma separated. Well, how would I go about doing that? Well, I could start out by saying for, and then we could say int I equal to 0, I less than, and then pause at it and think if you're making a mistake. Well, unfortunately, that's really old way of doing things. Fortunately, we could use a string, and then we could say name in names, for example. But even better than that, we could simply say, let's say uppercase for a minute equals names.collect. This is in Groovy, and I can say to uppercase. You can do this in Java also if you're interested. That shouldn't be very difficult at all. So we have an uppercase on our hand, and I want to print it, right? So when I'm done, I want to print it. So that's where I want to print the value. But how do I print the value that's in uppercase right now? Well, we could use this nice style, and we could say for, we could say something like name, and then we could say in uppercase, and we could print out the value. We could say, for example, name like this. Well, if you show this to somebody working with you, they look at this and say, good job, nice work, but can't you really have all those printed on the same line? And you say, not a problem, I can do that very easily. How about that? Well, but that's not the way we normally print stuff, do we? Oh, of course, not at all. We could probably put a little space around it. Yeah, but what about a little comma? Okay, we can put a little comma also. But then you notice there's a stupid comma in the very end. Now, how do you get rid of that stupid comma in the very end? And you are thinking for a few minutes. You're saying, this has got to be an easy thing to do. And I know what you're thinking. Maybe to print this in a string and then go back and remove it from the end. Maybe that doesn't appear too smart. And you spend maybe quite a amount of time, and finally you realize there is a way to fix it. And so the fix is going to be very simple. You go back and say, I don't want comma in the very end. So for int I equal to 0, right? How do you feel? Right? Anybody who has done this? Everybody. So look at the hands reluctantly going up. And I feel your hands go up and your heart sinks down. Right? I feel it. I feel your pain as a programmer. So we don't want to do this, right? This is just a very interesting operation, common operation. Life has got to be good to do this. So how about simply saying print line uppercase dot join and simply put a comma next to it? What do you think? Honestly, the day I learned about the join method, I cried that night, right? This is the way programming should be, abstraction for us to use, right? This is amazing. Well, you can do the same thing, thankfully, in Java also, because there is a join method on the string class. So, for example, let's go ahead and take this real quick and play with it. I won't go through the full example here in Java, but just to give you a highlight how this is going to look like, I'm going to go back to this code for a second. Let's go ahead and say in here, I want to take this main function, and I'm going to say here is my list of string. We'll call it names equals arrays dot as list, and I'm going to just go ahead and print out those names right here. But I want to print them comma separated, so I could say string dot join, and I could specify what I want to join with, for example. I could start specifying things like this. Alternately, what I could also do, for example, is if I have a collection on my hand, I could say names dot, for example, stream dot map, and I can say given a name, convert it to uppercase. So string dot to uppercase, which is the same method we wanted to implement on the other side. So now that I have converted that, I'm going to call a collect method, and I'm going to say joining with a string comma, and this is going to give us the value we are interested in. So I'm going to just output that value right there in here. Now for this to work, I got to do a little bit of an import work here. So I'm going to go ahead and say import stream.collectors and bring in the joining method as a static import right here. So we can go ahead and bring in some of these methods very easily into our code and work with it. So the collect method, basically in this case, I got a stream on my hand. I'm going to take the stream object. I'm going to map the stream into an uppercase value. So I'm saying perform the conversion of this to uppercase values. And then once you're done with the conversion, go ahead and collect that for me and join them as a result. And then when you finally get the result back, go ahead and print it for me. And that's what we are saying in this case. So we can see how it becomes very easy to express code. That's Java 8 joining. And similarly, string has a join method we could use as well. So we saw all of that, but let's step back for something even more fundamental. Now, when you're programming with object-oriented languages, I'm sure everybody in this room has read a good object-oriented design book. And what did the good design books tell us? Inheritance is bad, don't use it. Delegation is a lot better, and prefer delegation over inheritance. Now, we all read that book, and we said, absolutely, I completely agree with it. And then you put the book to the side, turned to your Java IDE and used inheritance. Right? Why did we do that? Well, that's because inheritance is easy to use. Delegation is so hard to use in Java. How do you use delegation in Java? Well, you have to first decide what class to delegate, and you got to type each of the methods by hand. You got to say, call the first function, route to this object, call the second function, route to the object, and then you say, is there a way to make the delegation faster? One way to make the delegation faster is to bring somebody who can type faster. Well, other than that, you could invent an IDE shortcut to make it faster. But both of those efforts don't pay off, because once you do it, if you inject a new method in the class, you gotta come and tweak it one more time. If you change the method name, if you change the parameters, if you change the return type, you gotta come and babysit this class. It becomes a liability. It ends up failing what's called the OpenClosed Principle. So what do? We quietly say, forget all of that, use inheritance, and let's praise delegation, but we will quietly use inheritance. What if delegation was really easy? Let's try it out. I'm going to create a class over here called worker, and the worker has a method called work, as you can see here. And in the work method, I'm going to simply say, let's just say working. So I have a worker method which is going to say working, and I want to just make sure I've not made any mistakes yet. Let's say Joe equals new worker, and let's just say Joe here, not job, Joe, and let's say Joe.work and call the work method. So seems like our Joe is just having fun working. Now let's create a class called manager, and as you would expect, this manager does absolutely nothing. And in this case, of course, this manager is a very smart manager. So the manager says, sure, why not? And you say def over here, Bob equals new manager, and you're going to say Bob.work. I know that's an alien concept for the manager, but we're going to still call that method bravely. But this manager, as I said, is very smart. So he says, delegate over here, worker, victim equals, and equals new worker, as you can see. And at this time, as you can see in this case, I'm able to call the work method on the manager, and you can see that just go through. So what's the magic happening in this case? Well, this is compile time metaprogramming, so almost any language with a compiler can actually do this. So what Groovy compiler does is it applies AST transformation at compile time and says, hey, look, you are delegating to this worker. I'm going to go to the class, the manager class, and bring over all the methods in the in the worker that are not currently available in the manager. Now, the question is, what's going to happen if there is already a method? Well, to understand this, let's go ahead and say we have another method called vacation. Now, what does the worker do on vacation? Now, we know what workers do on vacation. This is called code on the beach, and that's what the worker does. Now, the manager, of course, is very smart. Why would he want you to take a vacation? So basically, the manager says, of course, all year long, right? And so we have the vacation method on both. If you come to Bob and call vacation at this point, you would notice that it calls the manager's vacation, not the worker's vacation. And what is going on here? Well, it knows that there are certain methods already available in the manager, so it doesn't bring those methods. It only brings methods that don't exist. On the same token, if you have more than one delegate in the code, it'll bring all the methods from the first delegate. Now those methods become methods of the class, and at this point it'll only bring from the second class the methods that don't currently exist. So there is a priority order. The class takes precedence, the first delegate the second precedence, the second delegate the third precedence, and so on. So that gives us an example of how we can use a nice delegation, and this is very compliant to OpenClosed Principle as well, because if we go back and add a method to the class worker, that becomes available automatically in the manager class when we run the code next time, because the compiler would go ahead and ask it to be brought in automatically, knowing that this has been injected. So I talked about this nice delegation pattern. I want to talk now about pattern matching. This is one of the sweet things I really like about in Scala, in addition to a lot of other things, which is nice pattern matching capability. So think of a pattern matcher as a coin sorter. You have coins that you run over the coin sorter, and depending on the size of the coin, it falls through the first slot that fits it. And in a very similar way, a pattern matcher works through. Internally, a pattern matcher would create partially applied functions to do this, but let's look at an example. Let's say we have a process method over here. It takes a message, which is going to be, let's just call it as any object that's being given to us. I'm going to go ahead and say print line, and I'm going to just say process for now. We'll come back and fix it in a second. I'm going to call process with, let's say, a 1. I'll call again process with a 2. Let me call this again with, let's say, 1.2 or 3. And let's also call it with a string. Let's say, hi there. So this is good enough to start with. But I want to process these values separately. How can I do this? So I'm going to say message match. And in this case, I'll say case. And this is going to be an integer. And I will say what I got in this case. I'll say integer, right? Got int. How about that? So in this case, you can see it failed eventually because this is not handling all cases. An underscore in this context means a wild card, and then I will simply say got stuff. I don't know what I really got. So you can see it got int on the first 2 cases, got stuff on the second and the third, but I can go back over here and say case. In this particular case, we could say 1 and then specify print line, and we could say got 1. So you can see how it parses 1 out first of all, even though it's an integer, and if it's not a 1, it falls back to the second one, in which case it absorbs any integer, and then it falls through the rest of the things. Similarly, I can go back here, for instance, and I could say case. I could give a specific string, or I could simply say something that's a string, so I don't care what its internal name here is, and then I would say got stir, and you can see that it was able to bring in the string and give us the string object on our hand for us to work with in this particular case. So let me make sure that I'm dealing with this properly. So I'm interested in bringing in the string object that I want to use, in this particular case, the string object. Let's see, of course, the spelling error. I need to look at what I'm writing here. Great. So you can see in this particular case, it got the string object. I'll show you one other feature that I really like a lot. I have a process over here, but this time I'm going to say greet, and then I say hello, and end the greet right here. So what am I sending to this particular method? I'm sending an XML document, right? Well, not really. Notice the string around XML. We have been quietly doing this for a while, isn't it? Anytime you want to use XML in code, what do you normally do? You put a string around it. I mean, honestly, how would you feel if string was put around you all the time? No wonder XML misbehaves and creates all trouble for us, right? So Scala says, XML deserves some respect, just a little respect, right? So in Scala, you can drop a full XML, well-formed document into it, and notice it was able to accept it. But even better, you can go back over here now, and you can say, let's get rid of these guys for a minute, and I can simply say at this point, it says got stuff on both, but instead we will go back here and say case, and let's say greet, and we'll put some kind of a text we are interested in getting. We'll call it as what, and let's go ahead and say this is going to be the greet that I'm going to end. And then once we parse it, we can simply print out just the what itself, and you can see it says hello. So you can use an internal parser kind of a deal. It can process XML documents. It can work with XML as a first class citizen. I know that's a bit scary for us, but we can use XML, and we can even extract stuff from XML fairly easily. So pattern matcher is one of the things I really like in Scala, so it can be very effective to do some of those things. But going forward with this a little bit further, we can do this in Scala as well, but I want to show this to you in Groovy. So let's say for a minute, I want to take some languages. So let's say we have a bunch of languages on our hand, and somebody tells you to print an XML document with languages and authors in it. Now, for those of us who have written a code to spit out XML, how many of you want to go do more of that tonight? Not a single person. Maybe you're fresh from college or you haven't done it. You're like, can I do it? And then the minute you do it, you realize, why did I even say that I want to do it? And after doing it for a while, you'll quickly realize that code to spit out XML should be given to people in the prison, right? Nobody in the free world should be writing that code. Well, okay, it's not that bad after all. So let's take a look at how we can do this here. So I'm going to say builder equals new groovy.xml Groovy.markup builder. So Groovy provides a nice DSL, domain-specific language, to create these builders. So I'm going to say builder.languages with a plural, and that's all I've done so far. Notice as soon as I do this, a little XML baby just popped out. So it's very easy to write this kind of code, and we can say, well, how did this really work? Well, the builder is a DSL generator. It says, if you call languages on me, I don't have a clue what that means, so I'm going to give you the benefit of doubt and assume that you're talking about an XML element that you want me to use. So now that we have that, we'll go one level of indentation down, and I say language over here, and notice in this case it created a child element. Well, we could go a little further and say langs.each, and key comma value, and within this indentation we could put the language now, but it's smart enough to know that it doesn't know what language is this, so it'll treat it as an element. It doesn't know what a language is, it'll treat it as an element, but it does know what langs is because that's a variable coming from the outside scope, so it knows how to deal with it properly. So when I run this, you can see it created multiple child elements. Now of course I want to deal with the key and the value pairs, so the key is the language itself, so I'm going to say name : k, and it gives us the value of the name as an attribute for name, and then within this I say author, and then specify the value I'm interested in, and we can see how we can create an XML document with the attributes as names and then the values embedded within them, so it becomes a lot easier to work with. So you can write XML document very easily. Now the only thing you should remember to do is not to tell the boss that this is actually that simple. Tell the boss this is very difficult and you actually need a quiet place to work on it, and then take off to the beach or something, right? So that's the beauty of this. You can really do this very effectively, and you can work on this very nicely. Now, tail call optimization is another thing that I really enjoy quite a bit. Now, you can do tail call optimization in almost every language. Groovy does this through library support. Scala and Clojure do this through compiler support. And Java doesn't have tail call optimization. However, I was able to implement tail call optimization using Lambda expressions and lazy infinite stream collections. As I was writing the book, I kind of said, hey, I want to really experiment with this. So when I wrote the Java 8 book, I implemented tail call optimization in the library level. It was not too difficult. It only wasted about 4 days of my life, but was able to get that to work. But I want to show you how this works with Scala, just to kindle your interest on what this can do. Now let's take a little example to play with and see how we can use this. So let's say for a minute, I'll take a very simple example, factorial, and I want to find the factorial of a number. Let's say number n, I want to find the factorial of this. So let's take an integer. And how would I find the factorial? Well, we could say if n is equal to 1, return a 1. Otherwise, go ahead and return the n times factorial of n minus 1. So we could just call this and say factorial of 5, and we could run this, and we can make sure that it gives us the right result. Well, as much as Scala has type inference, it doesn't want to do that if the function is recursive, so I had to tell him what the return type is. So looks like that seems to be working nicely. Well, you will probably agree that recursion is one of the coolest concepts in programming, right? Because recursion allows you to implement a problem solution using solution to subproblems. How cool that is, right? You can express the problem as just a 2 or 3 or whatever n number of sub-solution to subproblems, and if you use recursion, people would want to hang out with you, right? They think you're really cool. So you have used recursion, you gather up a nice set of friends, and you're all partying and having a good time celebrating the recursions that you have seen. And you know this one guy that never likes you at work? He comes to your party uninvited and says, so you guys think recursion is cool, huh? And you say, yeah, isn't it amazing? And the dude says, really? Why don't you try that? And what's going to happen now? I heard Stack Overflow exception. Well, okay, my computer has a lot of memory apparently, but let me try one more time. Okay, even more. So we could try maybe a little longer, right? So yeah, it has a Stack Overflow exception. Now it blows up. And what happened? The party is over. Everybody has left. And you sit there, being hungover, and thinking, wouldn't this be cool if recursion actually worked? How sad it is, right? And you take another drink and cry a little bit more, and you say, why doesn't recursion work when you really need it, right? Well, wouldn't it be nice if recursion actually worked? But what's the problem? The problem is, if you look at the code we have on our hand, let's step back to 5 for a second, what's really happening? Let's take a look at this very closely. What's the last operation we do in this? Very tricky. A lot of people, when I ask this question, say it's the factorial. And guess what? I said the same thing too when I saw this first. However, the last operation that's really happening is the multiply operation. So what's happening in this case on line number 5 is you take the value of n on your hand and you wait with the operator multiply for the result of factorial n minus 1 to return. So you climb up one more stack level. So now you're on the second level of stack doing the same thing, waiting to perform the operation. You climb one more level until you hit the ceiling and then you blow up the stack. Wouldn't it be nice if you somehow can kind of step out of the function and then call it again, and then step out of the function and call it again? Well, this is very nicely explained in a fantastic book. You can just Google for these 4 letters, SICP, which stands for Structure and Interpretation of Computer Programs. In Structure and Interpretation of Computer Programs, or you just Google for SICP, you'll find it. And they talk about some really interesting way to look at program structures and execution. They talk about procedures. So they talk about procedures versus process. They define a procedure as the code we write and a process as the code that actually execute. Now, we all know this already. The code we write is not the one that runs. A lot of optimization, compilation, all that happens under the hood. So when you write an iteration as a procedure and you are running the iteration, let's say in your computer, it most likely runs as an iteration, no surprise there. When you write it as a recursion, it may run again as a recursion, no surprise there until it blows up the stack. But what if you can write it as a recursion and very quietly, because of some optimization, it can rewrite your code and run it quietly as an iteration? Then you got the best of both worlds, because you can express your code as recursion, but it would not take a toll and would nicely run as a iteration when you run the code, never to get a Stack Overflow exception because of that. So how do we do that? Well, that's where tail call optimization comes in. What it really means is that the last operation you perform in a recursion must be the call to the function itself. So in order to do this, what I'm going to do here is I'm going to go back to this code, and how do I make factorial the last operation? I'm going to say fact is going to be integer over here, and actually it won't cut it as an integer. I'll make it a big int because it's going to be rather a large value. So now that I have a fact as a first value, if n is 1, I'll simply return the fact. Otherwise, I will call the factorial one more time, but this time I will say n times fact comma n minus 1. If you notice the code structure now, notice in this example we have converted this in a way that the very last thing that happens in this code is a call to the factorial itself. Now we can go back here and simply say 1 comma 5 over here to call this, and we can see that it's performing this operation just fine. But what if I include a very large value in here, something along these lines? What's going to happen? When you run the code, of course, it is able to use this properly, and you can see, and don't try to memorize this. So it brings you the factorial value for that large number without throwing a Stack Overflow exception. And the dude that gave you the hard time earlier, you can ask that dude to memorize this number now before going home. So the point really is we can use a tail call optimization very effectively as long as the call to the function is the last call itself. The Scala compiler is able to optimize. There are certain limitations in Scala for tail call optimization because the JVM doesn't support tail call optimization, so there are some limitations they have to work with. This is also done in Clojure quite a bit. It has a recur method that can do recursion very nicely. You also can do this in Groovy through library support. They've done a fairly interesting thing in Clojure. And like I said, I played with these things before, so I was desperately trying to see if I can make something work in Java. After wasting 4 days of my life, I was able to actually implement it. So it's kind of fun to see these things kind of come together and we can have something working. Now, the last 2 things, if time permitting, I want to talk about is meta programming in Groovy. And this is one of the features that really draws me into Groovy. And the idea behind this is you can actually make this work really well. And tools like Grails or Gradle or so many other tools would not exist today and be so cool to use if it was not for metaprogramming in Groovy. But what is metaprogramming? Well, let's say we have a class called person, and I'm going to scratch the surface here. I won't have time to go through this fully here, but let's say we have a person class, and I have a work method on the person. Let's go ahead and say in here, we're going to just print out working. Now I can create an object, let's say Sam equals new person, and I can call Sam.work over here, and you can see that it is able to call the work method. But what if I say Sam dot, let's say play tennis, and if I call play tennis over here rather than work, it's going to fail. Now, how do I make something like play tennis work? And maybe I want to also make, play tennis call a few times, and then maybe I want to call play football. How do I make all this work? Now, rather than writing all this code, we could apply some conventions. Like what Grails does as a convention is, if a method name starts with the word find, then it would develop a SQL command to run on the database to get that object based on whatever property you mention. Like if you say find by first name and last name, it'll generate a SQL command to say select from person, whatever row where the first name equals what you provided and the last name equals what you provided. So they can generate all this SQL command and relieve us of the responsibility of that. So we can do some of these conventions. But how do I make all of this work? Because this is failing here, as you can see. So we're going to go back to this code and write a method called method missing, which takes a string name and an arguments. And within this method, I'm going to simply say, you called, and put a name as a printed value. Now, I call the method missing as the mother of all methods. It says, if you don't find the method, come to mama, I'll help you. So it takes the call, rather than giving you an exception, it handles it dynamically. Now, what you do within this method is entirely up to you. You can use some logic and convention and say, well, now that you call this method, I'm going to go ahead and dispatch this call and find out what to do. For example, in the case of Grails, it generates SQL command using GORM. In the case of Gradle, it can implement a task you want to execute or do other actions. More power to you based on what happens in that area. So you can do very powerful programming with metaprogramming. But here's the beauty. It's not an all or nothing proposition. I'm not a purist by any means at all. I'm as imperfect as any human could be. But I try to be pragmatic. So I would take Java applications, and where it makes sense, I would mix in Groovy, and I would do quick metaprogramming in those areas, and I can run my Java code surface into Groovy bytecode, Groovy generated bytecode, and then step back up into Java. So you can start kind of intermixing these language features where it may make sense, and you can benefit from it very effectively. So for the last about 3 minutes I have, without going into details of this, I'll share with you just one other feature that I think is pretty exciting. And this is a problem that is in a solution that's available in Clojure, but you can do this in almost every language on the JVM by borrowing these libraries from other places. And one of them is dealing with concurrency. Now, we know the problem with concurrency is when you have shared mutable variable, it becomes really hard to protect concurrency. Well, software transactional memory is meant to solve that particular problem. Let's see what that really means. I'm going to define over here. Let's go ahead and define for a minute. Let's go ahead and say this is going to be a balance of 0. And I'm going to go ahead and print out the balance value right here in Clojure, and you can see the value is 0. Now you tell me, hey Venkat, go ahead and change the value of balance. I have to admit, I don't think I can do that. And the reason is the variable balance is not a variable at all. It's a value. It's immutable. You cannot change it. So what Clojure says is, rather than changing these variables, it protects that into what's called a managed mutable identity, and such object is called a ref object. So I'm going to grab this code and wrap it into a ref object, and I'm going to say this is a reference. Now when I run this, you can see it is going to print out the details of the reference itself that it's going to bring in for us, not the object value per se that we're going to create on our hand. So once I create a ref object that I'm interested in utilizing in this case, how do I go about using the ref object that I want to define? Well, in this, I'm making a mistake obviously. Once I create a ref object here, I can ask for the details of the reference object, maybe using a little ampersand at symbol around it. This is a way to dereference the object to get the value out of it. Well, the beauty of this approach is this gives an opportunity for us to get a value out of a reference. The nice thing about value managed mutable identity is you cannot access this object unless you get into a transaction. So software transactional memory gives you a transactional boundary, and unless you're within the transaction, you cannot go ahead and modify this code, this particular variable. So you have to enter a transaction. What happens when multiple threads enter a transaction? Well, when multiple threads enter a transaction, if they don't compete for each other, they both can succeed. If they do compete for each other, then one of them would go ahead and finish, and the other one will automatically retry. I won't have time to show you the full example of STM here, but it's a feature that has drawn me into some really interesting ways of solving concurrency problem, which is useful when you have enormous number of readers, but very infrequent writers available for you. So you can use this kind of approach to solve some concurrency problems. You can use this in Clojure STM, or you could also use this, for example, in Multiverse API. Akka provides a certain set of features as well. So the beauty of this is, by learning some of these other languages, we not only can program in those other languages, but we can program in the language we are programming in already, and we can make really good use of some of these also very well. And that is one of the biggest benefits we see by really intermixing these languages. I've just shown you about 10 different things that are pretty cool here to do in these languages, but the real power is that the power is to us, the programmers. We have the freedom to choose the solution that makes the most sense, and all we have to shred is our fears that we have for these things. And once we are able to get rid of those fears, we have the right to try out things. If it works, we can keep it, build on it. Otherwise, we can ditch it and move on to something else. But I've noticed that there are certain things. The other thing that I really like about looking at these languages is it gives me a set of design tools that I never get exposed to programming in one language. But when you look at multiple different languages, you carry home with you when you go back a certain set of design tools that you never had before, and that leads to better innovation and better experimentation and also better programming overall. So I hope you like some of the features here, but I'm sure there are other features you will go explore on yourself and get excited about things that you can use with some of these languages on the JVM. Thanks for your time.